first speaker this afternoon is Jan Hązła, who is the German. Did I pronounce that right? No. Okay. He's the German research chair at AIMS Rwanda, and he's going to talk to us about intransitive dice and how to generate them. Jan, you know how to use this.
Good afternoon, everyone. Welcome after lunch. So yes, my talk will be on intransitive dice, which is a particular aspect of maybe a phenomenon that is sometimes called intransitivity. So what is that? Yeah, so hopefully most of us will know a transitive relation is a relation that satisfies the following axiom. If A is in relation in B and B is in relation with C, then A is in relation with C. So an intransitive relation is one which is not transitive, but usually intransitivity will refer to situations where somehow at the first glance you might think, oh, this should be transitive, and then you realize, oh, actually it is not. And in this particular talk, I want to focus on dice. Okay, so this is also maybe a little bit English language issue. So somehow I think the way, at least one convention is, it is one die and many dice. Okay, just that we are not confused. Okay, so what are they? These are those ones. Yeah, these are the objects that we can throw, we can gamble with them, or just use them in games of chance. However, since we will be doing some mathematical treatment, I will also be thinking of dice, but not necessarily these cubic ones, but also thinking even abstractly with growing number of faces. And yeah, the kind of the starting point is maybe a question how. So let's say that I have 3 different dice, and also what I am allowing to change is the numbers that I place on the faces. Okay. And then you can ask as a first question, how can we say that can we compare them somehow meaningfully? How can we say that one die is better than another one? And for that, let me propose the following procedure. So let me just consider, so let's say that I want to compare the blue and the yellow. So let me consider the procedure where I take the blue one and I roll it once. And then I take a yellow one and I also roll it independently. And then I read off the numbers and I say the one with a higher number has won. And then I just count in this random experiment what is the probability that the blue die is going to roll a higher number than the yellow die. Okay, so let's quickly count how it will go in this example. So, you know, when I roll the blue die, I have 6 possibilities. When I roll the yellow one, I have 6. So this is really just a simple counting. I have 36 possibilities. And if on the blue one I roll 9, then it will always win. So this is 6. Another 6 from the other 9. If I roll the 4, it will only win with 1. So these are another 2 possibilities. And if I roll 2, it also wins only with the 1s. Okay? So in total, out of these 36 possibilities, the blue die is going to win 6 plus 6 plus 2 plus 2 equal 20 over 36, which is strictly higher than 1 over 2. So in that sense, I can say that the blue one is better than the yellow one. If I am rolling blue and you are rolling yellow, I have like a positive expected value of having a higher roll. And then, of course, I can do it for the other pairs, right? So, okay, so this is as a summary. So probability that the blue one outrolls the yellow one is 5 over 9, which means I'm going to now call this situation that the blue beats yellow. I can do the same with the yellow one. Then you do the counting. Okay, believe me, 6 plus 6. Yeah, 8 and 6 wins everything. 1 always loses. No, 6 wins with 5 and 3. Anyway, it's 6 plus 6 plus 4 plus 4. When you compare the yellow and the green one, you will also see that it will adds up to 20 over 36. So yellow beats green. And finally, you can check the third remaining pair. So now green versus blue. Okay, 7 is winning with 4 and 2. 5 is also winning with 4 and 2. So it's 4 plus 4 plus 4 plus 4. 3 is just winning with 2, so plus 2 plus 2. And, you know, maybe surprise, surprise, you add it up. It is also 20 over 36 equal 5 over 9. So why is it surprise, surprise? I just found I just showed an example where the blue beats yellow. Blue is better than yellow. Yellow is better than green, and green is better than blue. So at least for me, the first time I saw it, this is surprising. I would expect that this relation of being better is transitive, but it is not. We just showed an example where you have intransitivity. Okay, this is maybe the main motivation for this slide is just that I can show the banknote they use in Rwanda with the gorilla. But somehow this now this relation, it has the following corollary. If you are, I don't know, if you are running a casino, maybe. Consider this game. The first player, so now let's say that I use exactly these 3 dice. The first player, I say, can choose one of those. So the first player can choose blue, yellow, green. Then player 2 can choose one of the 2 remaining dice. Then they both roll. And the player with a higher roll maybe is going to be paid 5,000 francs by the other one. And just, if you think a little, just an interesting point about this game is that now player 2 has a strategy with a positive expected value in this game. So if you play it many times, player 2 is going to, you know, almost surely make money, right? And the reason for this is, if I have this cycle, if blue is better than yellow, yellow is better than green, and so on, and I choose blue, then the second player can always find, okay, green is better than blue. So when I choose blue, the second player can choose green, and green is going to be better. If I choose yellow, the second player can choose blue, and so on. So for every dice, there exists another one which is better. So this is kind of an unintuitive game where the second player has an advantage. Okay, so that's something that I'm going to talk about very briefly. Like, so actually this problem has a connection to another problem which is a part of what is called social choice theory. This is Condorcet paradox. So this is another famous example of intransitivity, and it occurs in voting. And you know, this is maybe an example of a problem where, yes, you have a procedure to aggregate people's preferences that fails somehow. Okay, and this particular example, this is, you know, this is a real life example. Like, you know, for the ones of us which are old, like many years ago, there was this thing in politics in the United Kingdom, there was the Brexit, yeah? And there was somehow, it was a lot of confusion regarding this Brexit, like what did people really want? And this is one example of an opinion poll that was taken during that time. And people were asked, you know, there were 3 alternatives, basically. They said one alternative is just stay in the European Union. Another alternative was exit but use the deal. So May was the prime minister. Okay, so remain, exit without a deal, and exit with a deal. Okay, and then when they were polling people, it turns out that when you poll remain versus the deal, 56% prefer remain. If you poll no deal versus remain, 52% prefer no deal. And if you poll the deal without a deal, then 58% prefer a deal. So you have, again, you are choosing something, there are 3 alternatives, but every time the majority of people prefer one to the other in a cycle. You see, there is somehow no logical best choice in the situation. And I want to stress that this is not that, like, people in this poll, they were not behaving illogically. Each of them was asked, what is your first option? What is your second option? What is your last option? Each person was answering logically. The part where you get a paradox is only after you add up all of their answers. You see, and somehow, and it actually, in one of the papers, there is a connection also between this Condorcet paradox and this problem on dice that I am talking about today. Okay, maybe let me skip that. just a little bit, what is the story of this, of studying this intransitive dice? Because I think it is also a nice, maybe social story about like the social part of mathematics. So the examples, like the one that I just shown, they were known for many, many years. Yeah, they were studied 50s, 60s, 70s, and this was somehow like a folklore, you know? And relatively recently, maybe in the last 10 years, there is a question, how common are these examples? Are these just some special examples that you have to, you know, really think hard to come up with them, or maybe they are very common, maybe every time you take some dice they will be intransitive? And when you have a question like that, maybe the first step is, can you formalize it? You know, like if you want to do rigorous math, we have to somehow be more precise. So one reformulation, which maybe helps, will be, let's ask, is there a natural way to generate these examples? Are they somehow hidden, or can we easily uncover them? And also the other part that I already mentioned is, okay, if you try to do this mathematically, if you do this for finite n, okay, you get some numbers, but like they not necessarily like point you the right way, but maybe you get some insight if you also study the limiting behavior, maybe, for example, for large number of phases. Yeah, and what I find kind of cool about this, so I think the papers that somehow started it, they were, in terms of profile, very different papers. One of them was written by you know, some researchers in America, and at the time, I think like 2 out of these authors were high school students. And then this sparked interest of some, maybe, you know, more famous people. And in the following year, there was what is called the Polymath project launched about this problem, which also led to a paper. And you know, these Polymath projects, this is somehow an idea that has been tried in recent years to do mathematics in a little different way. And like some very, you know, very reputable people are involved in it, and even in this project there were some very, very strong people involved. But basically it's called collaborative mathematics. So it's like people collaborate like on a Wikipedia platform, more or less, or on a blog platform, and then they write up a paper, and then when the paper is finished, they don't write it down, under their names, they just say it's a paper by Polymath, and they publish it like that. No? Actually, I'm not sure it's been so successful recently, but at least like a few times this has been tried, and then there were like very strong papers that came out of this project. Okay, so let me try and just quickly discuss this question of how can we get these examples of intransitive dice in a more systematic way. So the first attempt would be maybe as follows. Okay, so let me maybe first set a stage. So what is this die for us abstractly? Maybe abstractly it's just an array of numbers, right? Like a die with n sides or n faces is just a sequence A1, AN. And now what does it mean? I said this intuitively, but what does it mean, this relation that A beats B? Well, you have to just count over all possible pairs ij, how many times AI is strictly greater than bj, how many times AI is strictly less than bj. Maybe there are some ties. Usually we don't worry about ties. And then if this number on the left is strictly greater than the number on the right, that is the definition that A beats B. Okay, so this is the relation we are studying. So maybe the first attempt to generate examples is like this probabilistic method. Just do it randomly. And what would be the simplest random model? For example, like this. Right? A random n-sided die is just going to be, you know, now this A1, AN is like a vector of n variables, and each of them is IID, independently, identically distributed, uniform in the interval 0, 1. So now the question we want to ask is, will this give us a lot of intransitive examples? So the mathematical way to say it is, if A, B, C are random dice, what is the probability, Pn, so n is now the function of the number of faces, that they are intransitive? And it turns out that this first attempt is not a good idea. If you take n to infinity, the limit of this number Pn is just 0. So they will always be transitive. And very shortly, let me say that this is because if you sample them IID at random, you can look at the sum of the faces. For every die A, you can look at the sum from I equal 1 to n AI. And you know, because we are sampling IID, this f of A as a random variable, it has some standard deviation. So if you sample 3 of them, they are going to have not exactly the same sums. And it will turn out that this causes transitivity, because the one with the highest sum is going to be the highest, the one with the lowest sum is going to lose to the other two. And okay, this actually, you need to prove it. This is not like super easy, but also not super hard. But somehow, on the high level, this is the reason that this is not a good model to generate examples. Okay, so the typical picture for these random dice I described is like this. Yeah, there is A, B, C, and then A is better and C is worse. Like this is not an interesting example. And as I said, it seems that this problem came from these phase sums. So the second attempt could be like this. Let's say that a random balanced die is going to be this random vector, the same distribution, faces uniform IID in 0, 1, and then it's conditioned on this sum being, let's say, equal to exactly the expectation, so n over 2. So let me remove the property that prevented me here. Let me just say that now I'm going to sample 3 times, and every time the sum is going to be exactly the same. I condition on this event. And you know, these people with the high school paper, that was somehow the first thing they or like one of the things they studied. And they didn't prove a theorem about it, but they ran experiments, and then they conjectured that it seemed to them that the probability that in this model you get an intransitive example is actually not 0, that it goes to like 25%. And this other paper by Polymath basically was devoted to proving this, this conjecture. And let's quickly think about, so what does this result mean? Like, why is it, so it's not 0, okay, so now we found a way to generate examples, but why exactly is it 1/4? So this 1/4, it somehow means that this model where you condition on the sum of the faces, it's like maximally chaotic. So first, it can be shown by some, you know, basic arguments that this probability of being intransitive for any model at all, it cannot be more than 25%. So 25% is the maximum. And also, if you think about it, that like one reason, that intuitive reason why it should be 25% is consider all possibilities of, you know, like putting this relation winning and losing between the 3 dice. Like you have 3 pairs, for each of them the arrow can go one way or another, so you have 8 possibilities. And 6 of these possibilities are transitive and 2 are cycle. So if you have the maximum chaos, so like each of those is equally likely, the probability of the cycle is going to be 2 over 6, which is 2 over 8, which is 25%. Okay, so in other words, maybe this is like a nice way to reformulate it for some people. If you kind of recompute the probabilities, what it means that if you condition on A beating B and B beating C, probability that A beats C just goes to 1/2, which maybe it is not very intuitive, yeah? Because I'm telling you A is better than B and B is better than C. That should give you, if I'm conditioning on that, that should give me some information that maybe A is a strong die in expectation and C is not so strong. But no, this probability gives me no, this event gives me no information whatsoever on the probability of A beating C. Okay? And very quickly, mention like, and this is somehow a very unstable phenomenon. So okay, so you can prove that you get it for these uniform random variables and you are happy. But a question that we asked in at some point was like, you know, how fragile that is. Yeah, and you can think, for example, about a slightly different model. Take this A to have exactly the same idea, but now the faces are IID not uniform, but they are Gaussian. They are just normal Gaussian. Now the expectation is 0, so you condition on the face sum equals 0. And it turns out that if you just change this uniform to the Gaussian, in the same setting, you are going to get that you will not get intransitivity. So it only works, like there is some reason that it only works for uniform distribution. And this is not just for Gaussian, it has to be uniform. Any other distribution basically is not going to work. And you know, okay, like with these problems, then you can also try and carry them forward a little bit. So another, you know, like maybe natural thing to think about is, so we had these 3 dice, and somehow they had these, like, they are chaotic, yeah? It's 25% that you get the cycle. Like, the suggestion then would be that if you take more, if you take 4, 5, 6, you know, you just do the same principle, like you think like what should be the expectation if you assume everything is completely random, and you would expect that now everything is just going to be random. And what is like an interesting twist is that this was also written in this initial paper. They said, okay, so for 3 it's going to be 25%, for 4 they just computed the proportion of these tournaments which are transitive, and they said, okay, the probability will be like that. But when these people in the Polymath did their simulations, like maybe a bit more precisely, they realized that actually if you take more than 3, this is slightly off. You don't get like perfect uniformity. Like there is some additional structure that is happening in there. So basically, if you now, for example, if you consider tournaments on 4 elements, you realize there are 3 kinds. One of them is like transitive, so you know everything is just ordered transitively. One of them is that you have a cycle of length 3, and then maybe one element which is either losing with everyone or winning with everyone, and one element which is like a full cycle of length 4. And what they observed experimentally is that this configuration is maybe slightly more likely than the other ones. And what we proved at some point is that, you know, we confirmed this conjecture, that indeed, if you take more than 4, you don't get complete, more than 3, you don't get complete chaos, you get a little bit off from uniformity. And this has even like another counterintuitive consequence. So now, okay, the number 48%, this I cannot prove. I just proved that it's less than 50. But experimentally, if I now condition that A beats B, and B beats C, and C beats D, and I ask what's the probability that A beats D, like, intuitively, you should say, okay, like this one is stronger, 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 so this probability should be more than 50%. In the chaotic case, we get 50%, and here it's just even the other way around. It's actually 48%. Yeah, so we get like a really counterintuitive conclusion if we take the cycle of length 4 somehow. Okay, yeah, so maybe there are other aspects, but let me skip those. Maybe one thing I would like to say is, so now, you know, how do you prove these things? And this is like, there is quite some delicate mathematics involved in that. In particular, you need central limit theorems, but you need very precise, very delicate versions of central limit theorems. You know, and the reason is, you can remember this definition, right? So how do I decide that one die beats another? Well, I have this sum bigger than this sum. Okay, so it's a sum, and these are, if A and B are random, these are going to be some random variables. So it sounds like something that should be fine for central limit theorem. But you see, it's a sum with n squared elements, but the randomness is coming only from, here it's n degrees of freedom, here it's n degrees of freedom. And remember, if I condition on the sum being equal 0, then this sum, then this random variable behaves completely differently when I don't condition. Yeah, so it requires like a lot of care in establishing these bounds in central limit theorem to carry these theorems through. Okay, to finish, I want to advertise 2 things. One is an AIMS essay, which like it's, I think for me, it's waiting to be written. So maybe it's not immediately apparent, but like the question that I am asking, these questions that I was discussing, they are related to the following one. For a balanced n-sided die A, you know, you can try and decide how strong it is with respect to all the other balanced dice. So I can let P of A to be probability that A beats B, where B is a random balanced n-side die. And the question is, I want to find among all balanced ones the strongest. So I want to take the supremum over A of this P of A. And these theorems I was showing, they imply that if this supremum is larger than 50%, then the number, the measure of the dice that have a supremum larger than 50%, it has to go to 0. But the question is, do they exist at all? So do there exist at all among these balanced dice any of those which are kind of that I can say that they are stronger than others? So like what is the limit as n goes to infinity of this supremum, you know? And it's some problem where first you have to simulate and like think about like what is the correct answer and then prove it one way or the other. And okay, if you want a more accessible treatment, this line of work, it was discussed also in a Quanta magazine. So there was an article published about it last year. And the last thing to advertise is, so if you like this sort of questions, or more generally, maybe probability, information theory, combinatorics, we are doing a summer school in August 2024 in Rwanda. There will be 3, I think, very good lectures coming to give short courses. So the applications are open until April 30. There is a website where you can read the instructions. So I also invite everybody who is interested to apply. Thank you.
All right, thank you very much. Any questions? Yep.
Very stupid question probably, but when you go back to the result where you say conditioning on A beats B, B beats C, probability that under this condition A beats C converges to 1/2, how fast does it actually converge? Like, is it a convergence when you go back still to, no, the one with only 3, but where you just had the convergence to 1/2?
Okay, I see.
Yes, actually this one, how fast is this convergence? Like, is it really, really fast when you do simulations for small n? Do you directly see it, or?
Yes, I mean, okay, like to prove, I don't know. If you do simulation, 1,000 for sure is enough, probably 100 is enough to believe that it's converges.
Okay, so it's really fast. Mm-hmm. Do you have like an estimate? You know, I would just, when I say like n equal to 10, just.
Yeah, 10 is probably not enough. No, very good question. You see, like that's another AIMS essay that can be written. I have never actually run, or like I have not thought about like what's the first
Convergence, yeah. Okay, interesting.
Thanks.
All right, there's a person over there.
This was a fantastic talk. Thank you, Jan. You skipped over the slide I was waiting for when I realized the connection to Condorcet.
Which one?
Saying which voting method with more than 3 candidates is fair.
The Condorcet.
Oh yeah, you see, like as I said in the panel, it's like I'm a negative person. Like I think you know, like one message of these results on Condorcet paradox is like there is no principled way actually, you know. It's not about the voting method, it's just how the way the world is. Sometimes we are in these situations where like you have this cycle and yeah, like I guess you should agree on a method in advance so then it doesn't become like this big squabble. That's like, but what exact method? There is no answer, like you need to have some values that go as input, you know, like it cannot be just like purely objective choice, yeah?
So what's the next slide?
On this?
Yeah.
I mean, okay, so sorry. So I didn't want to come too much into this, but basically, okay, so what is the relation between this Condorcet paradox and the dice? Is so actually, if you take like a natural model of voting, you know, like okay, there are 3 candidates, everybody has like an independent uniform ranking or something like that. And you compute the probability that you get the Condorcet paradox as the number of voter grows, you would hope that it will be like with the dice, that it's going to be 0. But it's not 0, it's 9%. And it's also, it's some constant of trigonometry. There is actually interesting math, like, okay, what is going on here? And you know, and so it means like these things, they actually happen, yeah? Like it doesn't happen maybe that we have 2 candidates and there is exact tie, but these problems, they really, this is a real life problem. I don't know if it has a real life solution. And maybe the connection to the dice that we investigated was So for us, somehow the situation with the dice is to get this intransitivity out, we had to assume that that this number of faces is, the sum of the faces is equal to the expectation. So like somehow by analogy here, we asked, so what is the probability that you get this Condorcet paradox if you also condition on the fact that the election is close? Because that is also like a feature of real life elections, right? Like at least in functioning the societies, you would like that the parties election is always close, because if the people don't like what you are saying, like you should reposition yourself so more people vote for you. And this is a little bit also present in real life. And the problem is that when you condition on the election being close, then the probability of this Condorcet paradox, again, it becomes even higher. It's from 9%, it goes to, again, 25%. So that's another pessimistic conclusion, I'm afraid. Huh?
And another AIMS essay.
All right, let's thank Ian. We need to transition to the next speaker. Thank you, Ian.